Greetings and welcome. My name is Alex Peterson. I'm from the Management of Complex Systems Department at UC Merced, and today I'm going to talk about when the scientists cross the line. If you thought I would be talking about something controversial, such as in these other works, sorry, but I only have time for this shameless plug. The actual topic of my talk today is mobility, yet there are actually various types, such as family, education, and work-mediated, as illustrated here by my historical trajectory. Today we'll focus on two particular mobility types, cross-border and cross-discipline, that are frequently encountered in researcher careers. In the first part of this talk, I will focus on cross-disciplinary collaboration and mobility. The definition of cross-disciplinary scholarship that we adopt is research demanding expertise from at least two distinct disciplines. Hence, this work seeks to better understand the dynamics and impact of cross-disciplinary collaboration by focusing on the groundbreaking research activity generated by the Human Genome Project in the United States, which started in the early 1990s. We recreated this ecosystem of biology and computing scientists by using faculty rosters from top 80 biology and computing departments in the United States. Based upon this researcher-centric dataset, we then tracked collaboration among these scholars within their home discipline and across disciplines. Hence, in this schematic, researcher A and C are cross-disciplinary because they each feature a publication including the other from the opposite domain. Shown here is the evolution of the collaboration network. Notice the increasing prevalence of cross-disciplinary scholars and the rich interface for knowledge sharing they develop. This interface also represents a social bridge by which researchers transition from being traditional CS scholars into bioinformatics leaders. We applied econometric methods to assess the impact of cross-disciplinary activity on career and project level outcomes. Model 0 above looked at the aggregate level of careers, whereas models 1 through 3 used publication level information and an author fixed effect specification to test for citation premium at the article level. Models 1 through 3 become progressively stricter. In the final model, we apply a course matching approach within author profiles. The career level model 0 indicates that scholars with 10% of collaborators who are cross-disciplinary are cited 6% more over their life course than monodisciplinary scholars from the same discipline. The article level models show that cross-disciplinary articles are cited 20% more than their monodisciplinary counterfactuals, even when counterfactual observations are matched on the same author as in Model 3. This researcher network highlights the most central researchers in the ecosystem, highlighting the mobility of several CS faculty who forged across the bridge to become elite faculty in the receiving discipline. One clear success factor is being able to speak a common language. Based on bits on the one hand and ATCs and Gs on the other hand, we hypothesize that this common language helped to overcome other cultural barriers and to establish a highly functional marriage. The Human Genome Project championed what we call the consortium science model, whereby teams of teams coalesce around common objectives, in particular, sharing benefits equitably within and beyond institutional boundaries. It took 13 years from start to finish to map just a single human's genome. Yet nowadays, anyone can mail a bit of spit and get a comprehensive genetic analysis back in a few months. Wow! In the second part of the talk, I will focus on cross-border mobility, exemplified here by the Nobelist mobility network, constructed using data from more than a century of Nobel Prizes. The crosslinks in the center of the network represent foreign-born Nobelists, those who received their award for work done in a country different than their birth country. For those of you that recognize the surnames in the initial world cloud, those were the native language surnames for all 202 foreign-born Nobel Prize winners. Also notable is the disproportionate fraction of cross-border links that terminate on the United States. Historically, 1 in 4 Nobelists in STEM are foreign-born, a frequency that has increased over time, largely benefiting the US and Northwestern Europe. Indeed, the migration of even a single laureate can have huge consequences in science, technology, and innovation in both the destination and the source country. This highlights the increasingly competitive international market for elite scientists. To measure the impact of mobility on research outcomes, we mined the APS article and citation dataset to identify when and where authors moved, and also to identify authors that did not move. Panel A here shows how we leverage the rich affiliation, keyword, and citation data available to not only disambiguate author names, but to also create location histories for each researcher. For those researchers who did migrate, we aggregated publication data for the 5-year period before and after the mobility event, as illustrated in Panel B. We then split the analysis into 3 periods to test for variations over time in the mobility effect. Within each period, we identified 3 groups of individuals. The group G1 is comprised of researchers who never moved prior to the end of the period. Group G2 is comprised of researchers who moved in a previous period. And group G3 identifies those researchers who moved within the target period. The objective of the counterfactual matching method is to identify the most similar non-mobile twin or doppelganger for each mobile researcher. For example, consider this mobile researcher A who moved in 1995. We then apply the propensity score matching method to fish through the non-mobile researcher pool and to identify the best match. Importantly, this search only uses the publication data from the pre-mobility period. Then, for each identified researcher pair, we estimated the treatment effect by computing the difference in a given outcome variable, y, computed for the post-mobility period. We computed differences for 3 types of pairs. The first pair is a placebo model, comparing groups G1 and G2, both comprised of researchers that were not mobile in the target period t. The second compares G2 and G3, comparing researchers that moved prior to t to those that moved in t. And the third compares G1 and G3, comparing researchers that never moved prior to t to those that moved in t. Our results show that mobile researchers gain up to 17% increase in citations relative to their non-mobile counterparts, an effect that appears to be increasing with each time period. Regarding a plausible mechanism, the citation premium is coincident with higher diversity of research topics, of collaborators, and of geographic coordination in the immediate 5-year period following each mobility event, indicative that researcher mobility serves as a positive disruptor of knowledge and collaboration networks. Together, these results provide additional clarity on the complex relationship between the mobility of human capital and the dynamics of social capital investment, with implications for immigration and national innovation system policy. Thank you for your attention, and if you feel like crossing the line in the near horizon, please contact me about exciting boundary crossing opportunities at UC Merced.